Welcome back. This is the day Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about rate orders. So rate orders are the idea that in a chemical reaction, not every single reactant has the same essential role as far as the rate goes. So now, every single chemical is important for the reaction. However, not every single chemical may have the same effect as far as the rate. You can think of it like on a sports team. You need, for soccer, 11 players to be on the field to have a team. But not every single player who actually is playing is as vital to the team's success. Some players might be better than others. And some players will have a bigger impact on outcome of the game too. So for example, if you played a soccer game and one team played with no keeper and the other team played with no forward, the team without the keeper probably still going to lose that game. He's a more important position than the other ones. So same thing with chemical reactions. Not every single chemical has the same impact on how fast the reaction takes place. So, but it's important that it's there, otherwise it won't take place. So again, it'll make sense as we go through this. So anyway, big idea, rate of reaction depends upon having the reactants and also on the concentration. If you change the concentration, you change the rate of the reaction. So when you think about the rate of reaction, it's basically this idea here. The rate of the reaction depends upon, well, how much A do I have? How much B do I have? And then how important is A and B? Some exponent that would tell us how important it is. Okay, this is just a generic expression to describe the rate. The rate equals the concentration of A raised to some power, B raised to some power, those powers being how important are they to the rate. And I'm sorry, in chemistry, there's a lot of K's flying around lately. This K here is the constant for the rate for the reaction, which means that every single chemical reaction has its own different rate at how fast it takes place. Example, iron rusting, very slow. Its K constant would be very small. The rate's small. Or something like burning propane, the rate's very fast, so the K would be very large. So in this class here, we're going to only have three exponents that are options, 0, 1, and 2. So you can have a 0th order, 1st order, or 2nd order reactant. Let me tell you about what that means here. So a 0th order reactant means that we need the reactant for it to take place, but if we change the amount, it does not change the rate. So for example, if you're working at some place like Dairy Queen or some other, we serve ice cream here. There's ice cream in the back, and then there's a worker at the front. And the ice cream plus the worker means we serve ice cream. That's the product. So you go to the store, the worker combines with the ice cream to give you served ice cream, making you a happy customer. If we double the amount of ice cream in the back storage area, does it make you get ice cream faster? No, the answer is not. So the worker can only scoop ice cream at a certain rate. And so doubling the ice cream does not change the rate at which we serve ice cream. So we would say that the ice cream is 0th order because we need it there to serve it, but having more of it doesn't really change the rate. For a 1st order reactant, this means that if you double the amount you have there, it actually proportionally increases the rate of the reaction. So back with our ice cream worker analogy, if we doubled the worker's presence, this would allow us to double the ice cream being served because every single worker scoops at a certain rate. And if we have 2 workers, now we're scooping twice as much, we can serve twice as much ice cream in the same amount of time. So if we think about the rates here, we would say like the ice cream, if it was the A, it would have a 0 up here, and we'd say the workers would be to the 1st. So 0th order means doesn't matter, it doesn't affect the rate, we still need it. 1st order means it proportionally affects the rate. And 2nd order here is going to be exponential, so squared. That means that if you double the concentration, it quadruples the rate. Again, I don't have a good example for real life things here because I'm sorry, just think of one, but you can think of this like maybe 2nd order, 1st order, 0th order. It could be like thinking about individuals on a team, and the success of the team. So some people on the team are like 2nd order, meaning like their presence is really important for the team's success. Like when they get on the field, it has a huge impact on what's going on, whereas a 1st order person, yeah, they're good, they can hold their own, but they're not a game changer. And 0th order, well, anyway, so, and rate laws is all about this idea like how fast does it take place with respect to individual things, okay? So again, our general rate is the rate equals some K constant, which is just unique to the reaction. Is it fast or slow? Then how much reactants we have. And people that care about this too are people like with fireworks. It's really important to know how long this fuse, how fast it burns, because if it burns too fast, bad stuff happens. If it burns too slow, bad stuff happens. You wouldn't want to have your artillery shell go up in the air and then come back down and explode on the ground. And so you need to know how fast that reaction takes place. It's also important for our body. How fast is this reaction taking place? If a reaction takes place too quick or too slow, that's bad. Anyway, so anyway, and this would be for every single reactant. Every single reactant would have some impact on this. So if you have like 3 or 4 or 5 reactants, you would have 3 or 4 or 5 reactants, each raised to their own power. So again, 0th means no change. Well, first means proportional. Second means exponential. In this class, these are the only options. When you go to higher levels of chemistry, you'll find that there's other options too. You could have something that's like actually 1.5 or 2 1/3. You can even have a negative rate order, which means your presence slows it down. So, all right. So how do you actually figure out how important something is? So in chemistry, what you do is you change the rates and change the concentrations, see how it affects the rate. And so you do a bunch of trials, see how much this influences the rate of the reaction. All right. This is really important too when it comes to medicine. It's really important when a doctor gives a dose to know how big you are, because the concentration of the dose, if the chemical is like second order, the dosage, knowing the right amount is really important, because if you have a dosage off by a factor 2, the rate of the reaction will be off by a factor 4, and for the body, that's bad. So if something is 0th order, then the dosage doesn't matter because the body will use it at the same rate no matter what. But if some chemical in some drug is 1st order or 2nd order, the amount they give you is really important, because it could be too little and nothing happens at all, too much, and you might not make it. So anyway, we figured this stuff out through trials and stuff. We figured out, okay, if we change this concentration to this, what's the new rate? What if we double this concentration? What's the new rate? So it's also important too that you have a fair trial. You only want to change one thing at a time. So, which is no different than saying, like, if I was playing for some NBA team with LeBron James, if I subbed in with LeBron James and we started winning, and then I subbed out with LeBron James and started losing, we'd come to the wrong conclusion that Mr. Love is helping the team win. All right, you only want to change one thing at a time. So only sub Mr. Love in, only sub LeBron James in, and keep it separate for a little while, just do a little bit of trial and see who actually has the bigger impact. So anyway, so CH4 plus 2O2, our sample reaction makes CO2 and 2 waters. And we have a couple trials we looked at where we changed the concentrations. So in trial 1, we had CH4 is 1, O2 is 1. We found a rate of 1. So then we decided to double the CH4 and kept the O2 the same. When we doubled the CH4, what happened to the rate? It also doubled. So if when you double something, the rate doubles, then we would say that's 1st order. Again, mathematically, this is what we're doing here, saying, well, what was the concentration here? What was the concentration of this one? What's the new rate? What's the new rate? What's this end power here? So in trial 2 versus trial 1, our concentration was 2 and 1. So this would be 2 over 1. So that's just 2 raised to some power equals the new rate, 2 over 1, n is 1. So, of course, you may not even need to do it like this, because in this class, it's either 0, 1, or 2. So 0, no change, 1st order proportional, 2nd order exponential. How does oxygen affect the rate? We're going to find 2 trials where only oxygen's change, but nothing else is. So trial 1 and trial 3, we keep the CH4 the same, but we change the O2. So when we doubled the O2, we doubled the rate. We'd say in this one, O2 is also 1st order. So to find the overall rate order, that's like adding everything together. So in the last example, we had 2 1st orders. So 1st order means a 2nd order, which means if we doubled everything, that'd actually be doubling the methane and doubling the oxygen. And since both those are 1st order, we end up being 2nd order. So another thing too is once you figure this out, you can find the value K for the reaction, going back to the original generic expression. Once you find the value K, then you can find out what you expect the rate to be no matter what the concentration is. So once you know what the K constant is, then you can determine what the rate of the reaction is in any situation. Let's do a couple more examples here. So we're going to find out how A, B, and C are influenced the rate of the reaction to make D. And so we have some trials here. So to find the rate order with A, we need to find out which trials we could use to just look at A and isolate A. So if you see that in trial 1, compared to trial 2, what have we changed? All we've changed going from trial 1 to trial 2 is we have doubled A. So going from here, point 1 to point 2, we have doubled A. We did not change B. We did not change C. So I guess we should say, so for A, what 2 trials are we using? We're using trial 1 and 2. And we see that with trial 1 and 2, what happened to the rate? When we doubled it, we doubled the concentration, and what happened to the rate? Looking at the rate here, the rate went from 5 to 20. That's not proportional, and it did matter, so therefore our only option here is going to be second order. It quadrupled the rate, which is 2 squared, which is 4. So that means that we are going to be A raised to the second power. So in our rate, when we talk about our generic rate expression, I'll just put it up here. Here we go. Again, our rate equals some K constant times A raised to some power times B raised to some power times C raised to some power. We just determined that the A's concentration is second order. So which means if we change A's concentration, it has a pretty big impact on the rate of the reaction. Now, how about we take a look at B? We got to pick a new trial, find out what trials we can use. We want to just change B with nothing else. So when I see trial 1 and I see trial 3, I see that for trial 1 and 3, we kept A the same. We didn't change A, we didn't change C, but we changed B. When we doubled B, the rate did not change. Our rate was 5 before. We increased the amount of B. We still have a rate of 5, which means that our rate here for B is going to be 0th order. It did not make a difference. Now, when we say something doesn't matter, we mean it doesn't change the rate. It's still important for the reaction, but it won't change the rate if you have more of it. Now, again, think of yourself as a business person. If you want to make your service faster, you would think about what things can I have a real big impact on the speed of my service. All right, if something doesn't change the speed of the service, you'd be wasting your money trying to speed that up. Okay, let's take a look at the last one. How does C affect the rate? What 2 trials could help us find out how C affects the rate? So we want to change C. So we see that C for trial 4 is 0.4. We need to find a trial that it compares to. So we can't use trial 1 this time because trial 1 to trial 4, we also doubled A. So we can't use that one. We're going to use trial 2 and 4. Why? A stays 0.2, B stays 0.01, C doubles. When we doubled C, write that down, trial 2 and 4 are the ones we're using. When we doubled C, what happened to the rate? We went from 20 to 40. We doubled C, we doubled the rate. So that means that for this one, C is going to be first order. So to find the missing rate, now we can pick any trial we want to and put the numbers in to find out what the K constant is. So this is the slow way, which you'll have to do this for some of the A-level questions. You want to do it here, but we will figure it out. So let's pick a trial to find out what the K constant is. Pick any trial we want to. We'll just pick trial 1. So looking at trial 1, we're going to put the numbers in. We actually have our rate was 5. This equals some K constant. Our concentration of A was 0.1 and it's raised to the second power. Our B is going to be 0.01 raised to the 0th power. And our C concentration is 0.2 raised to the first power. We're going to solve for what the K constant is, picking any trial, putting the numbers we actually have in here, find K. And that K will stay the same throughout the entire time. And then at the very end, once we solve for K, we'll look at trial 5. We'll be looking at for the rate. We'll have the K constant we solved, and we'll put the numbers we have in for that one to know what the rate would be, what we'd predict. So I'm going to real quick go ahead and solve for this one here. So 0.1 squared is 0.01. 0.01 raised to the first is 1. So 5 equals K constant times 0.01 times 1 times 0.2. The first is itself. Go ahead and get my calculator here. 5 divided by 0.01 times 0.2. Put that in parentheses. K constant for this reaction as given, 2,500. This is the K constant. Now, we can come down to this next trial, and we can put that 2,500 in that we just solved for. And now we can figure out what the rate is by just plugging it in. 2,500 times 0.4 squared times 0.08 raised to the 0th power again, which is 1, times 0.4 times to the first is just itself. I got a rate of 160. So when you plug all this in, we find that the expected rate for trial 5 is 160, would be the missing one. So again, this goes together. There would have been another way we could have done this as well, but you'll need to do this when you're solving it yourself. So we could have just compared this to another trial to see how it affected it. So if we see, we could just compare trial 4 and trial 5 and see what do we expect the new rate to be. So we see that we didn't change C. We changed B, but B doesn't matter. We know that B is 0th order, so we'll not change the rate. We doubled A. Well, how does A affect the rate? A is 2nd order, so if we double A, we should quadruple the rate. 40 times 4 is 160. We could have picked another trial. Let's compare trial 2 and 5. Again, we doubled A. When we double A, we should quadruple the rate. So 20 quadrupled is 80. B doesn't matter. We have to double, we doubled C. When we double C, we also double the rate. So we're gonna take this and times it by 4, then times it by 2, we get 160 again. So we are confirming that we found 160 properly. So when you wanna find a missing constant, what you do is you find the rate order for everybody, solve for K, picking any trial. Once you find the rate order, how they all affect it, you can just put their concentrations in. So here's A from trial 1, here's B's concentration from trial 1, here's C's from trial 1, and then you can find the missing K and then use that K for any other trial. Also, I should note that in this example, I have a 2nd order, a 0th order, and 1st order. You do not need to have a 2nd, 0th, and 1st every time. You might have 2 2nd orders. They're independent of each other. You might have all 0th order, you might have all 1st order. So it's not like in every chemical reaction you have 1 0th, 1 1st, 1 2nd. You can have any combination of there. Okay, let's do another one. These numbers aren't quite as nice. So I'm just gonna find the rate order for these things here by looking at the numbers and ask myself, is it 0th, meaning it didn't matter? 1st, it was proportional, or is it 2nd order, like when I changed it, it had a really big impact, more than proportional. So this is just hydrogen peroxide reacting with iodine reacting. So looking at trial 1 and trial 2, what happened? We doubled I. When we doubled I, because again, how do I figure that out? 0.01 to 0.02, that is twice as big here. We kept this guy the same. So trial 1 and trial 2, we're comparing how does I affect the rate. When we doubled it, what happened to the rate? 1.2 times 2 would be 2.4. It mattered, but it wasn't proportional, 2nd order. This actually quadruples. 1.2 times 4 is 4.8. So when we doubled I, it quadrupled. We're gonna say that I is 2nd order here. Now, how does hydrogen peroxide affect the rate? We gotta pick 2 trials to compare. We're gonna use trial 1 and 3. Why trial 1 and 3? Because we keep I the same in trial 1 and 3, and we only changed H2O2. So 2 to 4, we doubled the hydrogen peroxide. What happened to the rate? 1.2 to 2.4, we doubled that. We'd say this guy is 1st order. So this guy's 1st order, this is 2nd order. Let's take a look at another example. All right, the numbers aren't very nice for us here, but I think we'll be okay. So how does HBr affect the rate? So 4 to 12, what do we do? We tripled the concentration of HBr. 4 times 3 is 12. We didn't change O2, so trial 1 and 2, we're finding out how HBr affects the rate. When we tripled HBr, what happened to the rate? 2.2 times 3 is also 6.6, so they both tripled. We tripled this, tripled the rate. That means that HBr is 1st order because it was proportional. All right, now for O2, how does it affect the rate? We're gonna use trial 1 and 3 because trial 1 to 3, we triple the oxygen and we don't change HBr. So this is a fair trial for oxygen. When we tripled this thing, this didn't triple, it went up by more than triple. If you plug this in your calculator, 0.0198 divided by 2.2 negative third, you'll find that it's 9. So when we tripled this, this went up by a factor 9. 3 squared is 9, therefore oxygen is second order. But again, in this class, because we know it's more than proportional, it's going to be second order. All right. Hope that helps you find out how to solve for rate orders. Again, big ideas is you just need to see how does each individual reactant affect the rate. So find 2 trials where you just change that reactant and then see how it affects the rate. So again, your options are 0th order, I changed it, it didn't matter. 1st order, I changed it and the rate also changed by the same amount. Or I changed the concentration of this chemical and it had a bigger than proportional effect. That means it's 2nd order. All right, Godspeed.